What's up, AP Chem kids? How are you? Unfortunately, you have to see my face in this video. I don't know if that's good or bad, so if I pick my nose or do something like that, sorry about that. This is going to be over. I'm just going to do questions 1 and 2 right here of the 2018 International Practice Exam off of AP Classroom, so this should be assigned to you. You should be able to get into it. Look a little different when I do it, so. Here it is. Here's question 1. Elemental sulfur can exist in a ring called the S8 ring. So this is showing the bonds, not showing unshared pairs. The first thing it wants to do is how many lone pairs would each sulfur have on it? Well, remember, anything right at the stair step needs to have 8 electrons around it. So you got a pair of electrons there, a pair of electrons there. So you'd have unshared pair here, unshared pair here, unshared pair, unshared pair. Second question, based on your answer to part A, determine the expected value of the SSS bond angle in the S8 molecule. So wants to know what this angle would be. Well, think about it. There's an unshared pair and unshared pair. That means there's electron geometry, 4 pairs around it, 2 shared pairs, 2 unshared pairs, just like a water molecule. So electron geometry would be tetrahedral. Molecular would be bent between these. So remember, for tetrahedral, it's 109.5 degrees. It'd be a little bit less than that because of the unshared pairs. If we look at our answer key here, 109.5 is a fine answer. Anything your angle between 104, 110, 107.8 is the exact answer. It's probably the major bond angle you need to know is tetrahedral is 109.5. If there's unshared pairs, remember it cuts down about 2 degrees for each unshared pair. Write the electron configuration for the sulfur atom in its ground state. You can do shortcut, you can do normal electron configuration. Hopefully that is something fairly easy for you, but 1s2, 2s2, 2p6, 3s2, 3p4, or there's a shortcut one. Either one is fine. The photoelectron spectra for chlorine is in this table. So remember, this is the 1s2 peak, 2s2, 2p6, 3s2, 3p5, because it's a little bit shorter than that one. So that's your chlorine one. The electrons in the orbital of chlorine have a binding energy, at this X value here, at this X peak, have a binding energy of 273 megajoules per mole. So remember, that's the energy it takes to remove these 2 electrons. These have the highest energy because these are the closest to the nucleus, most Coulombic attraction. So here, identify the orbital and explain the difference between the binding energies in terms of Coulombic attraction. So I must want to say, what is this asking here? Oh, comparing chlorine and sulfur, I didn't realize that. Where's that at? The electrons in the same orbital of sulfur atoms have a binding energy of 239. So if we think about that, so this is the binding energy for chlorine. Sulfur, which would have 1 less proton, same number of energy levels, would have a little lower binding energy because it has less Coulombic attraction for its valence electrons because there are less protons, less nuclear charge. So you'd have to identify this as the 1s orbital, this peak, and explain that the lower binding energy in sulfur than chlorine is because it has 1 less proton nucleus, less Coulombic attraction. So read here, peak X represents electrons in the 1s orbital. A chlorine atom has 1 more proton nucleus than sulfur atom. Therefore, electrons in chlorine are more strongly attracted to the nucleus. And the binding energy of the 1s electron in the chlorine atom is greater than that of the 1s electron in sulfur. Again, fairly easy, I think. Peak Y right here corresponds to electrons in certain orbitals of chlorine atoms. So remember 1s2, 2s2, 2p6, 3s2. This is the 3p electrons. There are 5 of them for chlorine. On the spectrum, carefully draw the peak that would represent electrons in the same orbitals of sulfur. So the 3p electrons for sulfur would be a shorter peak because it's only got 4 rather than 5 in the 3p. And we got to figure out if it'd be left or right. Well, it's got less protons, sulfur does, so less binding energy, so the peak should be drawn in this area. Look here, there's the peak drawn for sulfur. Next question, an experimental student studies the kinetics of the reaction represented above. So here's our reaction. And it looks like they're doing, again, it's kinetics, so it's got some initial rates here. First thing, determine the order of the reaction with respect to S8. So we know the order with respect to this. Remember, the coefficient does not tell you the order of reaction. You look at your table and go, okay, the concentration of S8 tripled here, and the rate went up from basically 0.7 to 2.1, which would be 3 times bigger. So when this tripled, this is not changing. This also tripled, so it would be first order with regards to S8. Determine the value of concentration OH that was used in trial 3, considering that the reaction is first order with respect to OH, negative. Well, this is not changing here, so it looks like our rate is doubling. So this would also have had to double if it was a first order reaction for that to happen. Again, had this not changed, then we'd have kept, then it would be 0 order. Okay, but it's saying that's first order, so this doubling, this had to double. Next day, the student conducts trial 4, which is not on this chart, obviously, using the same concentrations of S8 and OH negative as in trial 1, but the reaction occurs at a much slower rate than reaction trial 1. So we're using these concentrations, but they end up with a much slower rate than this right here. Student observes that the temperature in the lab is lower than it was the day before. Using particle level reasoning, provide 2 explanations that help account for the fact that the reaction rate is slower in 4. Well, obviously there's no difference in concentration. The only difference is it was colder. So let's kind of read here what they write. The temperature was lower on the second day, so the average kinetic energy of the reactant particles was lower. Or lower temperature, lower kinetic energy. Therefore, there were fewer collisions between particles with sufficient energy to react. There's one example. Second one, since the temperature was lower, the kinetic energy was lower, and the average speed of the particles is lower. At lower speeds, the reaction particles collide less frequently. So you got to provide both those things. So one of them, temperature lower, makes kinetic energy lower, so less energy when particles collide. And then the second one, lower kinetic energy means lower speed, so there's less frequency of collisions. That was 7 minutes. I'm going to stop that right there. I'll do question 2 in another video.